Good day everyone. Today I'll be presenting an overview on my final year project which is on adaptive artificial neural networks for fault diagnosis. So my name is Salahuddin Al-Shami and my supervisor is Dr. Musab while my FYP coordinator is Prof. Tinia. So the content of this presentation includes the introduction, literature review, research objective methodology, results and discussion, conclusion and recommendation. So fault diagnosis, which is also known as detection and identification of faults, is very important when it comes to industries and engineering systems in general. This is because faults happen all the time in processes. And when a major problem happens, it usually triggers tens of alarms within seconds and it becomes very confusing to the operator what the root cause of the problem is. And if the operator is not able to source out the problem on time, then it might lead to catastrophic events which causes injuries and death, or it might cause damages to the products or the equipment themselves, and it leads to money loss. So how can we diagnose faults fast and reliably? Well, one way to do it is to use artificial intelligence. But AI is a huge field, so what specifically can we use? In this project, we are using artificial neural networks to diagnose our faults. So what are neural networks? Basically, neural networks are sets of algorithms that are modeled to mimic the human brain in recognizing patterns. So you can recognize this, and this as three without any problem, even though they are slowly written. And you can recognize a friend that you haven't seen in years, even though you have seen thousands of people after him. Uh, so how do these network function? Basically, this is a network, a neural network. And if you're trying to classify something or recognize something like whether an animal is a cat or not, you can input all the features of a cat and then the network will try to work out a relationship between each feature and the output, and it would make a correlation. This correlation is called the weight of the of the of the input to the output. So then when you train it with thousands of data, for example, of cats and other animals, then these weights will keep on updating until the appropriate weight is figured out to actually relate the inputs to the output with the minimum error. Also, the structure and modeling of the network helps a lot in training the data. So the research objective of this project is to design a neural network that can identify and locate faults accurately. So how to use neural networks in industries? Well, basically for this project, we first obtain the data, then we develop a neural network, then we train the model, then we test the model, then we finally export the model. So for this project, I designed a beverage plant which has a simple syrup input and lemon juice concentrate input, which both go to the reactor and they mix around. And then we have a cooling jacket here that is controlled by cooling water. And then the output goes to the heat exchanger, which is also controlled by cooling water. And the final cooled product is sent to a holding tank. So this is the constructed version, and this is the simple syrup container, and this is the lemon juice container. They go to the reactor, they mix around, and then this is the cooling water. It goes to the cooling jacket, then this is the outlet, and then the product goes to the heat exchanger where it is cooled down by the cooling water from here, and this is the outlet, and this is the final product goes to the holding tank in here. And all of the process is monitored by sensors. So we have here 12 sensors in total and two constant measurements. So basically we have 14 attributes. So this is the normal operating conditions, and this is the fault conditions. And so we have 12 conditions in total. One is normal operating conditions and 11 of them is fault conditions. And we have things like leakage in the heat exchanger, syrup heater failure, and valve failures. So what we do after we obtain the data is we try to develop a suitable network. And this works by trial and error until you try to minimize the total error of the network and minimize the misclassified instances. Then after that, you train the model with all the training data that you have, and then you test the model with new testing data. And then if you are happy with the final result, then you go on to the final phase and then you export the model. So running out the 12 conditions of the plant, I obtained 2,880 data, and here we have 14 attributes, and we have 12 false possible outputs. So this is the final structure of the network that I found to be suitable the most. So we have 3 hidden layers. Two of them have 14 neurons, while the third have 12 neurons. We have 14 inputs and 12 outputs. And the hidden layers activation functions is hyperbolic tangent. And I used the Cauchy-Newton method to train the network. So this is the history, the error history of the training method. So it started out high, and then it started to minimize until it reached a value of 0.002 in about 10 seconds. So it's a pretty good results. To further examine the results, I obtained the confusion table, which tells what is the predicted value of each output in opposition to what the real output is. So it shows if there is any misclassified instances, but in this case we have no misclassified instances. Then I moved on to the exported model, and first I tried to input single error. So the first error I put is the leakage in the heat exchanger, which could be confusing to the operator from a blockage in the same pipe. So whether it's a leakage in the pipe or a blockage in the pipe. But the system shows that it has no problem to identify it's a leakage with a value of 0.999. The second trial, I tried to introduce two faults. So I decreased the value of the heater, and I increased the value of the flow rate of the lemon juice. And as you can see, the system detected to be 0.61 probability for the flow rate change and 0.38 for the system heater, the syrup heater. And while it gave very minimal value to the rest of the value, so it actually just suggested to the operator that these two are having abnormalities in the operation. The third one, I tried to introduce a new fault, which is the lemon juice temperature. Throughout the whole throughout the whole project, I left out the lemon juice temperature constant. So none of the outputs actually developed a relationship with this particular input. So when I changed it, the results became very minimal to the normal operating conditions. So the system diagnosed it not to be operating normally, but at the same time no value was dominating, which suggests that it's a new fault. At the same time, it was showing the faults for a failure in the heater and a failure in the heat exchanger, which is impacting the temperature because it was sensing a different temperature. So the conclusion of this project is that we met the objective of this project, and we were actually able to we were able to develop a neural network that can classify faults accurately, and we integrated a model that is flexible with known data, unknown data, and multiple faults at the same time. For recommendation future works, I recommend that online diagnosis would be used and would be further investigated, since this one was offline diagnosis. I would all This can be achieved with the help of real-time data collection software. I also suggest that for future works there would be missing data, and the network should be able to diagnose the process regardless of this missing data. And then the third suggestion is that the system would be introducing continuously introducing new faults to the system, and the structure of the data should be updated constantly, and the system should heal itself and retrain itself based on the knowledge learned. The final suggestion is that neural networks could be used for anticipating the faults rather than detecting the faults. So that's all from me, and thank you for watching.